In this video, we're going to take a closer look at the eigenvalue eigenvector process. Right now, we did an example, and it was pretty much, from definition, this is, what the process looks like. And as far as finding the eigenvectors, there's not much we can do to streamline that process. We do have to go back and solve the homogeneous linear system, repeatedly for each eigenvalue that we found. However, in certain instances, it's actually relatively easy to find the eigenvalues of the matrix, right? There's some of our special matrices. If we have one of those special matrices, it makes finding the eigenvalues relatively easy. Not only that, but for the 2 by 2, there's a special form that the characteristic polynomial takes on. So let's start with that by looking at a general 2 by 2 matrix and seeing what sort of pattern comes out when we find this characteristic polynomial. So let's start with the 2 by 2 matrix A, B, C, D. Now remember, the characteristic polynomial is where we take the determinant of the A minus lambda I. So let's first write down what A minus lambda I is for the 2 by 2 case. And then here we have A, B, C, D. And then minus, distribute the lambda to the 2 by 2 identity, and we'll have lambda, 0, 0, lambda. And then subtract. So when we subtract, what are we going to get? Well, we'll have A minus lambda, B minus 0, C minus 0, and D minus lambda. So we have that, right? Now, the characteristic polynomial is what we get by taking the determinant of this special matrix, right? And we call that P of lambda. So in the 2 by 2 case, it's the determinant of what I just wrote down, the A minus lambda, B, and then C, and then D minus lambda. So let's do our 2 by 2 determinant and see what happens. So this is going to be A minus lambda times D minus lambda minus BC, right? So this is not typically how we write a polynomial, right? But let's go ahead and distribute everything and write it in the standard form. So we're going to have AD there, and then minus A lambda, and then minus D lambda, and then plus lambda squared, and then minus BC. All right? So let's write this in the standard form. So the lambda squared would go first, right? And then the middle term, I have in fact, let me write it like this. I'm going to take out the minus, and then I'm going to have the A plus D in parentheses, and then I'm going to put the lambda right here, right? So we have this. And then now let's look at the constant term. We have AD there, and then minus BC there. So we have AD minus BC. Wait a second. Let's say that again. AD minus BC. Now where have I heard that before? Oh, right. That's the determinant of the matrix. So the constant in our characteristic polynomial of a 2 by 2 matrix is just the determinant of A. Well, that's helpful. Not only that, look at the coefficient here, or the expression that I have in parentheses. That's A plus D. Well, A plus D is the trace of the matrix A. So if I know the trace of the matrix and the determinant of the matrix, it means I can write down the characteristic polynomial of a 2 by 2 matrix just by doing this. It's lambda squared minus the trace of the matrix times lambda plus the determinant of the matrix. And this result here is a very useful result. Now granted, it only works for the 2 by 2, right? But at the very least, we have a formula for our characteristic polynomial. So let's write this down. So this is a formula for the characteristic polynomial of a 2 by 2 matrix. All right? So that makes it fairly easy to work with, right? Now, so what would happen, if our matrix was a 3 by 3, right? Well, what would happen is we would have instead of a second degree polynomial, we would have a third degree polynomial. If our matrix was 4 by 4, we would have a fourth degree polynomial, right? So let me just make this kind of general observation. So in general, if A is n by n, then its characteristic polynomial, so P of lambda, is going to be, or let's just say is, an nth degree polynomial. Now, the formula for the higher dimension matrices, there is a formula, but it is not quite as straightforward as it is for the 2 by 2. It's kind of interesting though, because everything that we do for the 2 by 2 just seems to have this nice little special formula that we can utilize, right? So let me just do a quick example. Just finding the characteristic polynomial of a 2 by 2 matrix and then finding the eigenvalues. So I'm not going to find the eigenvectors, but just to show you how we can utilize this to at least streamline the first part of our process, finding the eigenvalues. So let's do an example. So here's our question. What are the eigenvalues? So what are the eigenvalues of our matrix? Let's say it is -2, 2, 3, -3, right? I mean, maybe sometimes the question just wants us to find the scalars. We don't necessarily want to find the vectors, right? So if we just want to find the eigenvalues of something like this, we can immediately write down the characteristic polynomial. So the characteristic polynomial of A is P of lambda, and it's always going to be lambda squared, and then we're going to have minus the trace of this matrix. Now the trace of this matrix, let me write it in, it's -2 plus -3 times lambda, and then it's going to be plus the determinant of the matrix. Now the determinant of the matrix is going to be 6 minus 6. So this matrix, the determinant is 0, so this is actually a singular matrix, right? And it doesn't matter if the matrix is singular or not, this formula always gives us the characteristic polynomial. So this simplifies to, we have our lambda squared. Now in parentheses here we have a -5, right? But then there's a negative in front of that. So that makes it a plus 5 lambda and then my constant term happens to be 0. So then the roots of this characteristic polynomial are in fact the eigenvalues of my matrix, right? So the eigenvalues of A, right, are the roots of P of lambda. So we get to another, big problem in math that involves finding the roots of some function. How many times have we done that? Right? So our lambda squared plus 5 lambda, set that equal to 0. And then now this is easy to factor out a lambda. And then we have a lambda plus 5 left over. And then we have lambda equals 0 or lambda equals -5. Now, it's not a coincidence if you think about it. Because the determinant of the matrix ended up being equal to 0, right? That's what led us to, well, first of all, we don't have a constant term here, or we could say the constant term is 0. And then it made it easy for us to find the roots. And in fact, one of the roots in that case is always going to be lambda equals 0. And in fact, that's an important characterization of an invertible matrix. See, if the matrix is invertible, your determinant won't be 0, and then lambda equals 0 won't be a root. Right? And this is actually a really big theorem, right? And again, we're kind of illustrating it with this 2x2 case, but let me state this theorem, right? Let's say, so A is invertible if and only if lambda equals 0 is not an eigenvalue of the matrix. So is not an eigenvalue of A, right? So if the matrix has a lambda equals 0, then it means it has to be a singular matrix, right? So that's another way that we can tell if a matrix is invertible or not. Now, obviously, this is not the easiest way. For especially a 2x2, all we have to do is check the determinant, which again we saw in this case that it came out to be 0. All right. So we have a nice formula for the characteristic polynomial of a 2x2 matrix. We have this nice relationship between invertibility and eigenvalues, right? Now let's up the ante just a little bit and say, well, what if we have like a triangular matrix, right? So now let's make it a 3x3, right? So consider A equals, now I'm going to write down a general 3x3 upper triangular matrix like that, and then we got our 0 there, and then A2 2, A2 3, and then 0 0, A 3 3. All right. So let's write down what the characteristic polynomial for this is going to be. So this one is going to be A minus lambda I, but now the I is going to be the 3x3 identity. So we're going to have our A1 1, A1 2, A1 3, 0, A2 2, A2 3, 0 0, A3 3, and then minus. Now when I multiply the 3x3 identity by my constant, I'm going to have the lambdas on the main diagonal, right? Because in the identity matrix, all I have are 1s on the main diagonal, when I distribute my scalar, those ones turn into the scalar. So as usual, what happens is we end up having just the elements on the main diagonal, and then we subtract lambda from those elements, and then because of all the zeros elsewhere in the matrix, all the other entries are 0. So it ends up being this. So A11 minus lambda, and then A12, A13. Then we're going to have 0 times A22 minus lambda, and then A23, and then 0, 0, A33 minus lambda. All right? So that's the matrix. Now to find the characteristic polynomial, we have to find the determinant of this. But what is interesting is we started with an upper triangular matrix. We subtracted this diagonal matrix. Well, it's still going to be upper triangular. And we know how to find the determinant of a triangular matrix. You multiply the elements on the main diagonal. So if we do that here, this is what we're going to get. We're going to get A11 minus lambda. My minus sign looks a little too curvy there. So A11 minus lambda times A22 minus lambda times A33 minus lambda. Right? Now, there's no need for me to FOIL this out because it's already factored. Right? So the eigenvalues are simply the roots of this. Right? So the eigenvalues these are found by solving this equation, taking our characteristic polynomial, setting it equal to 0. But we don't have a lot, you know, if we're not clever, you know, we could make this a very tedious problem, but it's already factored for us. That's the beauty of it. That's the beauty of just multiplying the elements on the main diagonal. So what this means is either A11 minus lambda is equal to 0, or A22 minus lambda is equal to 0, or A33 minus lambda is equal to 0. So solving this equation, I get that lambda is equal to A11, or lambda is equal to A22, or lambda is equal to A33. Now how convenient is that? That for a triangular matrix, let's go back up, and there's our matrix right there. The eigenvalues are the elements on the main diagonal. The A11, A22, and A33. Right? And this works not just for the 3 by 3, it works for any triangular matrix. So let's take that as a theorem. Right? So many useful theorems here. So let's take a look at this one. So if A is an n by n triangular matrix, then the eigenvalues of A are simply A11, A22, dot, 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 ANN. So we don't even have to go through the problem of finding the characteristic polynomial. If once we recognize that our matrix is a triangular matrix, all we have to do is identify the entries on the main diagonal, and those are our eigenvalues. I mean, that's pretty convenient, right? Okay, So let's do an example that involves a 3 by 3 matrix, but let's deal with the matrix that's triangular, and that way we get to use this particular result, and we see what the process is like when we have a 3 by 3 matrix, right? So this example might take a little while, but let's work through it. So find all eigenpairs of, and here's our matrix, 2, -1, 0, 0, 1, 1, and then 0, 0, -1. Right, so there's our matrix A. And when it says all eigenpairs, so we first have to find all the eigenvalues, and then for each eigenvalue, find the corresponding eigenvector. All right. Now, because A is triangular, we can write down right away what the eigenvalues are. There are these 3 numbers on the main diagonal, right? So half the problem, out the door just like that. So since A is triangular, its eigenvalues are the numbers. So I'll say lambda equals 2, lambda equals 1, or lambda equals -1. Right? So again, we're just looking at these entries on the main diagonal. We don't have to write down a characteristic polynomial. We don't have to solve any polynomial equation. Simply use the fact that the matrix is triangular and we have our eigenvalues. So now what we have to do is now solve the homogeneous system, right? So what I'm going to do is I'm going to write up the general form of the homogeneous system, and then we will solve that system for each of the 3 values of lambda, right? So the system that we have to solve to figure out the vectors now is of this form. It's A minus lambda I. That's the coefficient matrix. And then the V will be the vector that we're solving for. And then it's always going to be homogeneous, right? So let's write this in the matrix form so you can see it. So the A minus lambda I is going to be 2 minus lambda, -1, 0, and then 0, 1 minus lambda, 1, and then 0, 0, -1 minus lambda. So that's going to be the coefficient matrix, and then we're going to augment it with the column of zeros. So that this is essentially the system that we have to solve, but we're going to have to solve it 3 times, 1 time for each eigenvalue, right? So we can say, so let's start out with the lambda equals 2, right? So when lambda equals 2, now something interesting happens in this case. I don't think we've had this up to this point. We've never had all zeros in the first column, because if we plug lambda equals 2 in, it's going to eliminate that entry, but then everything else in that column is 0. So we're going to have to make sense of this. What does that even mean? And then we'll have the -1, and then when I plug 2 in here, I'll have 1 minus 2, so that's -1. Then I'll have a 0, and then here I'll have a 0, a 1, and then -1 minus 2, that's -3, and this is what our system looks like, right? Now, some of these systems will look a little bit different than before. Again, like I said, not having a pivot at all in the first column, what's up with that, right? Nonetheless, this is why we have those echelon forms, right? So I'm going to go ahead and put this in an echelon form and see what happens, right? Okay, so the first thing I will do is I will multiply the first row by -1. So I'm going to do this. So I'm going to do -1 times row 1. And then I'm going to also get a pivot here, right? Multiply the third row by -1/3, right? So -1/3 times row 3. All right, let's see what happens. So that's not going to change our first column, right? And then this becomes a +1, and then we still have zeros here. And then here I'll keep this as -1, and then 1, and then 0, and then I have 0, and then 1, and then 0. All right. So what does this tell me? This tells me that V3 has to be equal to 0. And then this equation tells me that V2 has to be equal to 0, which is the same information from the first row. So right now I don't have any information about V1. But that's because there is no pivot in the first column. So remember, if a column doesn't have a pivot, then what it means is that variable is free. So V1 can be anything, but V2 has to be equal to 0, and V3 has to be equal to 0, right? So the interesting thing about this, we don't have a pivot here, but remember what that means in our echelon forms, right? We have a pivot in the second column, we have a pivot in the third column, but we don't have a pivot in the first column. So what this means is V1 can be any real number. That's our free variable, right? We have to have at least one free variable no matter how big the system is. If we're solving for an eigenvector, right, we're always going to get a free variable. So what does the eigenvector look like here? They're vectors of this form. Any number in the first component, but then the second and third vectors have to be equal to 1. If we do that little trick of factoring out the t, then we're left with this as kind of our standard vector, eigenvector, that's associated with lambda equals -1, right? So let's write down that first eigenpair. So our eigenpair, in this case, when lambda equals, actually lambda equals 2 is the one that we just did. So our eigenpair is of the form 2, comma, and then the vector is 1, 0, 0. All right? There we go. So then let's repeat the process and say, well, what happens when lambda is equal to 1? Okay, well, let's see. Again, we're going to get a fairly simple system, but again, it's just a matter of how we interpret it. So when lambda is equal to 1, the homogeneous system becomes, so plugging 1 where we have all the lambdas, so we'll have 1, -1, 0, 0. Then we will have 0, 0, 1, 0. And then 0, 0, -2, 0. So this one, I mean, it's very easy to interpret. So both equations here are telling me that V3 is equal to 0. Right? These two equations are telling me the same information. Now here, I don't have a pivot in the second column, right? My pivot here is, I have two pivots. Let me circle them. right? I could use this 1 and eliminate the -2, right? But again, it's still going to give me the same information. So I'm not even going to reduce it completely, but these are my two pivots. There's no pivot in the second column. That means V2 is now my free variable. So V2 can be any real number. And if V2 is any real number, then it means V1, when we move that over, it's going to be a positive t, right? So then the eigenvector in this case looks like this. Any number there, same number there, and then 0 there. So now when I factor out the t, this is the form of my eigenvector, right? 1, 1, 0, right? So then the eigenpair in this case, so the eigenpair for when lambda is equal to 1, then my vector is of the form 1, 1, 0. All right. So 2 out of 3. We have one case left. So let's see what happens when lambda is equal to -1. Like, what strange form is it going to have then? Well, we just have to write it down and see. So when lambda is equal to -1, scroll down a little bit more here. Plug in -1 for all the lambdas, and we're going to have a 3 there, -1, 0, 0, and then 0, 2, 1, and then 0, 0, 0. So this one is probably most like the systems that we've gotten up to this point, where we get our row of zeros at the bottom, right? Now, so what this means, right? And again, it's in a triangular form. It's not necessarily in the echelon form. We can get it in the echelon form quite easily by multiplying the first row by 1/3, and then the second row by 1/2. We can do those simultaneously, and then that gives me the system 1, -1/3, 0, 0, and then 0, 1, 1/2, 0, and then no change to a row of zeros at the bottom, right? So this is not quite reduced row echelon form, right? Because we have a pivot, but we have a -1/3 above it. Well, if we wanted to see what the RREF looks like, so all we would have to do is take 1/3 times row 2 and add it to row 1. So take 1/3 times row 2, add it to row 1. That produces our RREF, right? So we're going to have 1, 0. Now, that means I'm going to get 1/6 right here, and then 0. And then the second row stays the same. 0, 1, 1/2, 0. And then a third row filled with zeros, right? So there we can definitely see our free variable. So now the V3 is our free variable. So V3 can be any real number. That means V2 will be -1/2 t, and then V1 will be -1/6 t, right? So then here is the eigenvector. So it's any vector of the form -1/6t, -1/2t, and then t. And if I factor out my t, then I'm left with this kind of, they call it a basis vector, right, for all the eigenvectors. So it's -1/6, -1/2, and then a 1, right? So the eigenpair in this third and final case, so our eigenpair is, so for this constant of -1, right, the vector is -1/6, -1/2, and 1. Now, let's say you didn't want to write down a vector with with fractions. Any scalar multiple of this would work. So let's say if I were to multiply this by, let's say, a -6, here's another way I could represent the eigenpair. So I could say, or, like if I just really dislike fractions, if I multiply this, because remember, t can be any real number. So what if we let t be equal to 6? Then the eigenvector is going to be -1, -3, and 6, right? So you can take any scalar multiple of an eigenvector to get another eigenvector, right? So I'll just say that here. So any scalar multiple of an eigenvector is another eigenvector. The only thing you're not allowed to do is to multiply by 0. Going back to the definition of an eigenvector, it has to be non-zero. So in fact, maybe I should put that here. Any non-zero scalar multiple of an eigenvector is another eigenvector. All right, so lots of really useful information in this video, some of which will definitely streamline the process. But I wanted to end with an example, like with a 3x3, just showing that even though it might be very easy to find the eigenvalues of certain matrices, finding the vectors will come back to solving systems. The system will always be homogeneous, that's a given, right? And we'll always end up with at least one free variable, so we have to make sure we, again, can identify what columns are pivotal and what columns are non-pivotal. And based on that, we can come up with our eigenvectors. All right? See you in the next video.